Hello everyone. In this video, I will review some of the basic facts about complex numbers, and let us start at the very beginning. So, complex numbers were introduced as a natural extension of real numbers, and they were introduced primarily to ensure the solvability of polynomial equations. To understand this, let us look at the equation x squared negative 1 equal to 0. We know by simple arithmetic that the solution to this equation will be the two values x equal to plus or minus 1. And a solution here means that when we substitute the value in the equation becomes an identity. In fact, when we substitute 1 or minus 1, we can clearly see that the equation will become 1 minus 1 equal to 0, which is indeed an identity of real numbers. However, if we try to do the same for the equation x squared plus 1 equal to 0, we will see that we are stuck at a problem, which is that x is, when we do the arithmetic operations, we obtain that x squared is equal to negative 1. And we immediately see the problem here is that there is no real number whose square is going to be a negative number. So, however, the equation x squared plus 1 and similar equations arise in a lot of applications. So we want to have a meaningful solution and, more importantly, a meaningful interpretation of this equation. And here starts the story of complex numbers. We formally define the solution, one solution to this equation, by denoting the square root of negative 1 as a new quantity, and we give it the symbol j. So we define j to be equal to the square root of negative 1. Having introduced this new quantity, which we call an imaginary number, we see that the solution to this equation then becomes the solution to the equation x squared equal to negative 1 then becomes x being equal to plus or minus j. And in fact, the square root of any negative real number will be an imaginary number. Let's say the square root of negative 7. This is in fact equal to the square root of negative 1 times 7, which is equal to square root of 7 times j. And in fact, the set of all real all imaginary numbers consists of a real number multiplying the imaginary number j. So we can write that imaginary number is a real number times j. This is real. Having introduced this new quantity, let us see how useful it is. Let us try to see if we can solve all equations using this, or we can express solutions to polynomial equations using this new quantity. For sure, we can solve the equation x squared plus 1, right? Because that's the whole point of introducing j. This equation will have the solution x equal to plus or minus j. However, let us try to solve the equation x squared plus x plus 1 equal to 0. this is another polynomial equation, right? Because on the left-hand side, we have a polynomial with real coefficients, and on the right-hand side, we have 0, which is a polynomial of 0 degree, right? We would like to be able to solve this equation. Let us try to apply the quadratic formula for solving quadratic solutions, quadratic equations, right? The quadratic equation, the quadratic formula of the solution will give us -1 plus or minus square root minus 4 divided by 2. We immediately recognize 1 minus 4 as -3, and the square root of that is going to be an imaginary number, right? And -1 is just -1. However, the sum of an imaginary number and a real number, we have not yet defined that. These are two different objects, meaning that we can not do something similar to this, that 1 plus 2j is not equal to 3, nor that 1 plus 2j is again not equal to 3j, right? In fact, in order to properly define this object, we have to keep the two numbers intact, meaning that complex numbers, and here we introduce the definition for the first time, complex numbers are basically the sum of real numbers plus imaginary numbers. Here, A and B are both real. All complex numbers can be written in this form as the sum of a real number and an imaginary number. And in fact, this can be encoded in a symbolic form by writing that the real part of z, which is a complex number, is equal to a, and the imaginary number of z is equal to the real number that multiplies j in the expression for z, which is in this case b. Let me get a new page, and so now we can perfectly solve all quadratic equations, right? Because if we have any quadratic equation of the form ax squared plus bx plus c equal to 0, we know the solution immediately will be x is equal to negative b plus or minus square root b squared minus 4ac divided by 2a, right? And in fact, it turns out that we might come across some problems where b squared minus 4ac turns out to be a negative number. However, that is fine now because we know that the square root of a negative number is an imaginary number, and the sum of an imaginary number with a real number is a complex number, right? In fact, it turns out that complex numbers have very natural operations that we usually perform on real numbers, such as multiplication, division, addition, and I will come back to that later in this video. However, they have one important property that real numbers did not have, and that property is the so-called algebraic completeness. And this is just a fancy word for saying that any polynomial equation of degree n, which is something of the sort an times xn x to the power n plus an minus 1 times xn minus 1 plus yada yada plus a1 times x plus a0 equal to 0, any equation of this sort is guaranteed to have n complex roots or solutions. This property was not valid for real numbers, as we can immediately tell that x squared plus 1 equal to 0 has no real solution. So we see the usefulness of complex numbers is, or the immediate benefits is to be able to provide meaningful solutions, as we shall see later, to polynomial equations. Now, moving on, it turns out that complex numbers, as I said, have a pretty good visualization, in the sense that we can actually plot or visualize complex numbers. For that, let me add a new page. And so to visualize complex numbers, we draw the plane, the Cartesian plane that we use to plot functions, real functions, right? On the horizontal axis, let us write the real part of the complex number that we're trying to plot, right? And on the vertical axis, let us write the imaginary part. Okay. Now, any point in the plane, let us say, for instance, this point will have two components, right? We'll have a horizontal component and we'll have a vertical component. This vertical component, this horizontal component, my apologies, is in fact A, which is the real part of the number Z. And the vertical component is B, which is the imaginary part of the complex number. And a complex number is essentially a directed line, or basically a vector from the origin to the point which represents the complex number, right? This is one form to represent complex numbers, which is so-called the rectangular form. You can see it's rectangular because while drawing or visualizing the complex number, we kind of draw a rectangle, right? There is another form to represent a complex number, which is called the polar form. And if you recall from your calculus class, the polar representation of the plane consists of any point in the plane is essentially the distance between the point and the origin and the angle between the positive horizontal axis and the line drawn from the origin to the point, and this is theta. In this representation, a complex number can be written as, and I'm writing this as a notation, R, and then we write an angle bracket, and then we write theta inside. This is another representation for a complex number, and it's called the polar representation of a complex number. A third representation for a complex number is called the exponential representation, which is that Z, the complex number, is equal to R times exponential of J times theta. And this representation, in fact, has deep meaning in which I'm not going to cover in this video. However, I will point you into some resources that you might find interesting in this regard. So R is in fact, as you can see from geometry, is equal to, like, this is a right angle triangle, right, and this is B. So we can see that R is going to be equal to, by Pythagoras rule, is going to be equal to the square root of a squared plus b squared, right? So, and this is always a real number, right? Because when you square, a and b are real numbers, and the square is going to be positive. So, and the square root of a positive number is again positive, right? So R will always be a positive number. And theta, as you can see, we can solve for theta in terms of B and A from the triangle here, right? We can write that theta is equal to tan inverse, right, of B divided by A, right? Because tan of theta is equal to B divided by A, correct? Now, I want you to try and do this on your own. I want you to express B and A in terms of R and theta. You have to be familiar with how to convert between the polar, the exponential, and the rectangular form of complex numbers. That will come. That will be handy later on. Moreover, as I promised, complex numbers have the same, very similar arithmetic operations as real numbers. For instance, let us say that we have two complex numbers, z1 being equal to x1 plus y1 times j, and z2, which is equal to x2 plus y2 times j. The sum between these two numbers, z1 plus z2, these are two complex numbers. Their sum is basically the sum of the real parts, that is going to be the real part of the sum, x1 plus x2, okay? And this is the real part of the sum, and the imaginary part is going to be y1 plus y2 times j. The sum of two complex numbers, we expect it's going to be a complex number again, right? Similarly, the subtraction as well. We can just put a minus sign here, minus sign, and minus sign, right? Now, let us try to multiply two numbers, right? Let us multiply two complex numbers, z1 times z2, right? We can write this formally as x1 plus y1 times j plus x2 plus y2 times j. And we can expand this bracket, right? We can expand the bracket to obtain that x1, x2, right, plus x1, y2, j, plus y1, x2, j, plus y1, y2, j square, right? However, we know that j square is equal to -1, right? So this is in fact equal to x1, I'm sorry, let me erase this. Okay. This is equal to x1 times x2 minus y1 times y2. And this is the real part of the multiplication of two complex numbers. Then we add the imaginary part, right, which is basically x1, y2 plus y1, x2 times j, which is obtained by just collecting these two terms, right? This is the multiplication of two complex numbers. However, if we try to compute the division of two complex numbers, let's say z1 divided by z2, it's not clear how exactly to do this, right? One way to do this would be to obtain the polar representation of the two numbers, right? And for that, in fact, let me add a new page and let's see how it goes. Now, suppose that our two numbers have the two polar representation. Let me do that time. Let us suppose that our two numbers, z1 being equal to r1 times the exponential of j times theta 1, and that z2 is equal to r2, right, multiplying e to the power j theta 2. Now if we try to divide these two numbers, say z1 divided by z2, this is just equal to r1, right, e to the power j theta 1 divided by r2 e to the power j theta 2, right? So this is just equal to r1 divided by r2 multiplying e to the power j theta 1 minus j theta 2. So the new number, the new complex number we obtain is r1 divided by r2 to the power e times e to the power j times theta 1 minus theta 2. And in fact, in polar form, not exponential form, we can see that if z1 is equal to r1 theta 1 and z2 equal to r2 theta 2, then z1 divided by z2 is going to be equal to r1 divided by r2 times theta 1 minus theta 2. So you can immediately recognize the importance of polar and exponential form, because some operations are much easier to perform in these forms, right? Like addition and multiplication. And similarly, raising to the power. Like, for example, we can say that z1 to the power k is going to be equal to r to the power k times k times theta, right? You can verify this formula for yourself. Now, I want to leave you with some food for thought, right? Oftentimes, when we try to do something, it doesn't come for free. Like, there's no free lunch, right? There is a very important property that real numbers had, which complex numbers do not quite have. Try to guess what it is property that we lost when we gained the solvability of polynomial equations. All right, thank you, and let me know if you have any questions.